Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at Chem Advantage.
This is a nice problem involving stoichiometry, and it's got some important concepts that you should really get used to and they'll be using for the entire year. We're taking an interesting compound, ethane, C2H6. Eth is a prefix that usually stands for 2 carbons. If you have any organic compound with the name eth in it, ethanol, ethane, ethene, ethyl ether would end up having 2 carbons involved in it. It's got 1 carbon, a 2nd carbon, and 3 hydrogens on 1 carbon and 3 hydrogens around the other. It's found in gas wells mixed with methane. There's quite a bit of it around in terms of our solar system. The largest moon of Saturn, Titan, of having huge lakes the size of Lake Superior containing a mixture of methane and ethane. Ethane has a boiling temperature of about 180 degrees below zero. This would be a chilly dip. Tough to swim in too because the density of ethane is about half that of water. So you should only wade in there and have an insulating suit. But let's get back to the problem. We're going to take this ethane as a fuel, combine it with oxygen to make carbon dioxide and water vapor. Here's the balanced reaction. 2 ethanes, 7 oxygens. So you need quite a bit of oxygen to produce all these carbon dioxides and waters. Here's where we start. We start with 84.6 grams of water that is being produced. And we'll be able to find out about all the amounts that would be involved in making 84.6 grams of water. If we burn this ethane and condense the steam, now the first thing to do, of course, is we have grams. And one of the first things that you've learned in chemistry is mass doesn't really tell us about what molecules do. We need to end up knowing about the number of particles, moles. And by now, it should be like almost second nature. Okay, I got 84.6 grams of H2O. The molar mass is 18.02 grams per mole. I can just change that into moles. We take 84.6 grams and divide by 18.02 grams per mole. The grams will cancel out. Moles will be our new numerator. And there's our conversion. Let me enter and see that we have about 4.69 moles of condensed water. And that makes sense. Our moles will always be smaller than our grams. So let me just put those moles in there, put that answer in. 4.69. I'm going to bring up the calculator again. Now that we have one amount of moles, we can find all the moles in a stoichiometric reaction. I mean, that's sort of the secret. You have 1 molar amount and a balanced reaction. Everything else is going to be proportional. In terms of weight, we're not sure what's going to happen with weight because we've got all sorts of these different molar masses. CO2's certainly more massive than our water molecules. So right now, let's just ignore the grams and deal with just the moles. Notice that 6 water molecules, 4 carbon dioxide molecules. So when this is produced, our products, we get actually less carbon dioxide than we get water. How are we going to find out our moles of CO2? We know they're going to be less. Well, here's the secret. You know the moles of water and the coefficient of 6. So I'm going to take that coefficient of 6. I've got this answer here in my calculator. I'm not going to retype it. And just divide by 6 to get it down to 1. If we reduce this to 1 water, we get 0.7682. And I'm going to do something here, though, if you've got a calculator, it's got a memory. You might as well not be using that memory. As this answer, 0.782, is going to be used in all the rest of my calculations because I'm going to use it as the basis to get CO2, O2, and ethane. So it's going to be an important number. I could write it down and retype it in over and over again, but most calculators end up having a storage feature where I can take this answer and store it. Now, you could use an alphanumeric thing, but here's a real quick trick. I can just store it as X. From now on, if I type in X, I get 0.782463929. I mean, stored to the accuracy that this calculator can figure out. And that's going to be really convenient. I said that knowing the amount of water, we can figure out the CO2. To do this proportion, I divided by 6. Reduced it down to this 0.782. And now turn it up back up to 4. So all I've got to do is take this reduced value. I'm going to have that as my entry. And I'm going to take my reduced value x, and I'm going to multiply it by 4. This calculator realizes that if you've got a letter and a number next to it, it's going to be a multiplication. And here it is. There's our answer, 3.13 moles. Now, don't ever put all these numbers in. You never have any answer with that much accuracy. So I'm just going to put in the 3.1, round it off, 3 moles of CO2. Let me see if that makes sense. We've got 6 and 4. Here we got 4.7 and 3. Yeah, the moles are smaller. That would be the right ratio that we would expect. We can take that last answer and change it into grams. I've got this 3.129, and I'm going to multiply it by the molar mass of CO2. We're going to be using water so often and CO2 so often that you'll remember their molar masses, 18 and 44. So just take that last answer. I'm not going to retype it in, and then multiply it by the 44. And if I want to be really accurate, even though I don't need that total amount of accuracy, I'm going to get the grams of carbon dioxide. That's 137.7. Even though there are fewer moles of carbon dioxide in water, the weight's greater because the CO2 has a higher molar mass. Fewer molecules, but each molecule weighs more than double. We would get 137.7 grams of carbon dioxide when we make 84 grams of water when we end up burning ethane. I want the rest of this, and again, once I've got the mole amounts and I've got the coefficients, I can find the rest. I can take my 4.69, divide it by 6, and then multiply by 7 to get the amount of water. But fortunately, I remembered that division, so I'm just going to end up doing my x times, let's see, how much oxygen was that? 7x, enter, and we should end up getting the moles of oxygen. That'll be the 5.48. 5.48. And let's double check to make sure we didn't mess up. Indeed, we have 7 O2s and 6 H2Os, so we'd expect a little bit more oxygen in terms of moles than water, not grams, moles. And yes, that makes sense. And we should have more moles of oxygen than CO2. In fact, if you took this 3.13, divided it by 4, and multiplied by 7, you get 5.48. That would be another way of solving this. In fact, if we took this 5.48 and divided it by 7 and then multiplied by 2, we would end up getting the ethane. Now, I guess a general rule would be divide by the coefficient you know and multiply by your new coefficient. But remember, I have my x as this division of water moles by 6, so I can just take x times 2. Make things fast. And we should get 1.56. And let's see, we'll put that number in here. We can find out the grams in both of these cases. In fact, actually, I should have taken this 5.42 while I had it in my calculator and multiplied by 32. And I should have had this 1.56 while I do have it in my calculator. Let me pull that up. My 1.56, let me multiply it by the molar mass of methane, again, to get from moles to grams, we multiply. So I'll take that last answer. I don't have to type it in again. I can just type in times 30.07, and I'll get my grams of ethane. Yep, 47.1. Now, this is sort of interesting. I forgot to multiply this 5.48 times 32, and I could do it on my calculator. But notice, what's the total mass of our products in this? Well, if you take 137.7 and add it to 84.6, you're going to get your 222 grams. I sort of rounded off here. I just really only needed 3 significant figures for my WebAssign problems. Even though our moles and molar masses and everything else are sort of weird in terms of numbers and follow ratios, you can be always certain that if you start with a certain mass of reactants, then produce products from them, the mass isn't going to change. I mean, the atoms have been rearranged. I mean, here we have this, ethane now changed to CO2 and change the water and the oxygen combined into both of those, but the mass is going to be the same. The total mass is still going to be 222 grams. So if I were to take this 222 and subtract 47.1 from it, I'll get 175.3. Let's double check that. In fact, this is one of the ways to find out if you did things right. Do your mass of reactants equal the masses of products? And if they don't, I mean, within rounding errors, you did something wrong. Go back and say, oh, what did I do wrong? Well, let's just do a little double check and see if we get this 175 for our 5.48 grams of oxygen and multiply it by, again, this is the molar mass, you'll remember, 32, a nice easy one. And let's see if we get that 175.3. And it's 175.4 if we round it off. But actually, this should have been 5.47724. And I bet you if you kept it unrounded here, you would have gotten exactly the 175.3. Well, there's our stoichiometry. And the bottom line of stoichiometry is whatever moles you have here in the actual amounts of your experiment, they're going to follow the same pattern as the coefficients in the balanced reaction. All the time. That's certain. And you can also just look at the estimates here. We have the fewest amounts of ethane. That's the lowest number of moles here. We've got the greatest number of moles of oxygen that were used. And again, that is the 7, and this 5.48 is bigger than all the rest of these. So always look your numbers over to make sure they make sense. I mean, these aren't abstract things. These are measurements of stuff, and they'll make sense if you use a table like this.